Let's say two particles are magically entangled by magic. Then they're separated by several light years. You change something about one of the particles, and something changes about the other particles. Magically, we've solved the problem of faster than light speed travel and broken all of causality in the universe. This is not what particle entanglement is about. Find out what it's really about on today's episode of Quantum Basically. Okay, so the deal with that first bit is that this is how people try to simplify particle entanglement, and I don't think it's a very good explanation, so I'm kind of making fun of it. Here's what particle entanglement is really about. Let's say you have some sort of interaction between two particles. Now, if you've studied any physics at all, you know that there are certain quantities that need to be conserved. For instance, energy. You have to have the same amount of energy at the beginning and the end of an interaction. Momentum's a really important one. You have to have the same amount of momentum at the beginning and end. Let me use an example that maybe you've heard of, maybe you haven't, but I think is a little bit simpler to work with in this case, and that's spin. In really simple words, spin is exactly what it sounds like. It's a little bit weirder than that if you really dig into the quantum, but it is something that needs to be conserved in quantum, so it's something we can use an example. So we have an interaction between particles, and let's say the starting spin is none, no spin. So after this whole interaction has gone down, we know that one of the particles is going to be spinning clockwise, and the other one's going to be spinning counterclockwise. We know that that has to be what's happening. But here's the thing. Remember all that stuff I talked about indeterminacy? It's not really that one particle is spinning clockwise and the other one's spinning counterclockwise. What's going on is that both of them are spinning clockwise and counterclockwise at the same time. They both have a mishmash of probabilities of being spinning clockwise and counterclockwise. And it's not just that we don't know, it's that literally that information doesn't exist. They're not spinning one way or the other. They're spinning both and neither. It's kind of a state of being both at the same time until you measure it. Once you measure it, you force that probability to collapse. And then it's either spinning clockwise or counterclockwise. Great, no problems. Now you take these particles and you separate them by some distance. You separate them by a mile or a million miles or a zillion miles. A zillion isn't a number. That doesn't matter. You separate them by any distance you want. And then you measure the spin of one of the particles. And let's say you measure it, and as that probability collapses, it decides it's going to be spinning clockwise. Well, that means the other one has to choose counterclockwise. And they didn't talk about it before. All we know is that one has to be spinning clockwise and the other one has to be spinning counterclockwise once you measure them. So once one has been measured to be clockwise, the other one has to be measured to be counterclockwise. And it doesn't matter how far apart you are, this will always be the case. It's almost as if the particles were able to communicate with each other instantaneously. So in a way, they kind of are communicating faster than light. Kind of. But it's not really something we can use to send information because we can't choose to make that particle spin clockwise or counterclockwise. And if we interfere with it such that we force it to spin one way to try to affect the one that's way across the galaxy or whatever, we unentangle the particles. What that means is that those particles, it's now no longer true that one has to be clockwise and the other one has to be counterclockwise, because all those laws that forced it to be so, we messed with that. So all we mean by being entangled is that the state of one is dependent on the state of the other. That's all. And that's only true because they were in this nice little closed system where they had an interaction all by themselves and there's no other particles interfering with them or getting involved in this spin dealy. It's kind of hard to do this whole thing without unentangling the particles. How do you even get those particles to be really, really far apart from each other without messing with one of them so that you unentangle them and now it's interacted with other particles in your system or whatever else? How do you measure the spin without unentangling it? This whole thing is kind of a work in progress, but it's incredibly cool. And it's for good reason that in science fiction, when people want to have faster than light speed communication, they're often working with entanglement. This is the last big concept that I'm going to be working with, but I sort of wanted to talk about some of the implications of quantum theory, so be there for that next week. Subscribe if you don't want to miss it.